in this problem, we have 15 bars, 15 chocolate bars, and we have 10 children that we need to distribute these bars to. And the question asks how many ways there are to distribute these 15 bars to the 10 children given certain constraints. So the first constraint in part A is that the bars are fungible, meaning they're non-distinguishable. So because they're non-distinguishable, what matters is how many bars each child has, not which bars each child has. So if we imagine that the children are these boxes here, then what matters here is how many dots are in each box, not which dots they are. And so we'll recognize this as the setting for the Einstein-Bose computation technique. So we know the answer is going to be n plus k minus 1, choose k, where n is 10 and k is 15. So the answer is 24, choose 15, or equivalently 24, choose 9. Now moving on to part B, the constraint is that not only are the chocolate bars fungible, but each child must receive at least one. So the bars are fungible, and each child must receive at least one bar. So the way to do this is, again, because the bars are non-distinguishable, what matters is how many bars each child gets, but we know that each child needs to have at least one bar. So we place a bar in the first child's box, a bar in the second child's box, and so on, and a bar in the 10th child's box. So now in total we're left with 5 bars to distribute. So again, we're in this Einstein-Bose computation method, where now we only have 5 boxes or 5 bars to distribute amongst 10 children. And so this gives us a total of 14 choose 5 such distributions, which is equivalent to 14 choose 9. Moving on to part C, we're told we're in the same situation as part A, so the chocolate bars are now not fungible. So we're in the opposite situation of part A. It matters which bar a particular child gets. So the way to think about this using part A is to say, okay, let's say we're in the same scenario as part A. Each child has, so child 1 has 1 bar, child 2 has 2 bars, and let's say child 10 here has 10 bars, or 4 bars. The difference is each one of these bars are now distinguishable, so we can label them like so, for example. And now it matters which bars are assigned to which child. So once we've distributed the bars to the children, we need to count the number of ways to permute the bars amongst themselves. And since there are 15 bars, there will be 15 factorial permutations for each distribution of the bars that we found in part A. So for each answer in part A, we're now going to have 15 factorial permutations that we need to account for. And finally, moving to part D, we're told that the bars are now distinguishable and each child must receive at least one. So bars are distinguishable and each child must receive at least one. One bar. And we're given a hint to use inclusion-exclusion. So the way to think about this problem is to say, okay, what are the total possible ways of assigning the 15 bars to the 10 children, disregarding the fact that each child needs to have at least one bar? Well, each bar has 10 choices, and there are 15 bars, so that's 10 to the 15th power. Now, out of these, we need to subtract the number of distributions where at least one child does not have a bar. So whatever the number of these distributions is, however many there are, we need to subtract them from the total number. So how can we compute how many such distributions there are? Well, let's make a definition. Let's define AI to be AI to be the event that the ith child, this is the set rather, that the ith child has no bar. So AI is the set of all possible distributions of these 15 bars such that the ith child has no bar. So if we look at the union from 1 to 15, since we have 15 children of AI, this is exactly the set of distributions where at least one child has no bar. So the union of these sets AI is exactly the set that corresponds to at least one of the children not having a bar. So if we can compute the cardinality of this union, that's exactly what we need to plug in here. So how do we compute the union of the sets? Well, we know we can use the inclusion-exclusion principle, and we know that the cardinality of this union can be computed using inclusion-exclusion using the following method. We can say, well, let's sum up I from 1 to 15. And this I is going to keep track of the number of students that do not get a bar. So inclusion-exclusion, we know that the sign keeps on alternating, so we're going to need a -1 to the I plus 1th power here to alternate the sign from plus to minus, etc. Now, how many ways are there to select I students out of 10 that will not get a bar? Well, there are 10 choose I ways. Now, once we've selected these I students that will not get a bar, how many distributions are there of the 15 bars that do not assign a bar to these I students? Well, each bar now has 10 minus I choices of students to go to, and there are 15 bars. So that's 10 minus I choices per bar for 15 bars. And so we get this summation, which calculates the cardinality of this union, which we can plug in here to get our final result, which is 10 to the 15th power minus the sum I from 1 to 15, -1 to the I plus 1th power, 10 choose I, 10 minus I to the 15th power.